Okay, so you've been building AI models. Maybe you've even got a cool generative AI demo running. You've seen the magic, yeah.
Definitely. The potential is huge.
So let's be real, taking that notebook concept, that initial spark, and turning it into something production ready, something that handles real users, real data, real scale, and, real problems, that jump is massive.
It really is. A demo often just, it calls a model, shows a result.
Yeah.
Simple. But a production system. It has to be reliable, safe, efficient, maintainable. You find out pretty quickly that just hitting a model API, well, it isn't going to cut it.
Right, you need layers,
Yeah.
components, an actual architecture.
Exactly.
So in this deep dive, we're going to try and cut through the noise. We've looked at a stack of sources, articles, papers, practical guides to pull out the essential building blocks, the architectural patterns you need to get your head around when you're putting Gen AI to work for real.
Yeah, we'll look at why those simple approaches just fall short and how adding specific layers step by step transforms that cool idea into, well, a dependable foundation.
Think of it like moving from building a prototype car in your garage, which is cool, to actually designing something that can handle real traffic safely, efficiently, day in, day out.
Good analogy.
Yeah.
It has to work reliably in the messy real world.
Exactly. We've pulled insights from sources talking about AI engineering, building robust foundations on cloud platforms, these emerging patterns in Gen AI, and responsible design guides. So let's dive into how you actually build up this architecture, starting with the most basic picture possible.
Okay, so the simplest setup, conceptually, like figure 10.1 in some sources, is super straightforward. A user sends a query.
Yep.
It goes straight to a model API. Could be OpenAI, Google, Anthropic, maybe one you host yourself.
Right.
And the response just comes straight back.
Yep.
Minimal. Easy to code for a quick demo.
Seems efficient. Like, why complicate it? Where does it break down first?
The immediate critical failure point, especially with external APIs. Data leakage, it's a big one.
Data leakage. So you mean sending private stuff out?
Exactly. Sending private or sensitive information outside your control, outside your organization.
How does that actually happen, though? Is it like someone trying to steal data?
Not necessarily. Often it's accidental.
Hmm.
An employee trying to get help summarizing a document, and they paste sensitive company info into the prompt. Or a developer includes maybe confidential policy details in a system prompt by mistake.
Right.
Or maybe the AI uses tools to access internal data, and that private data gets swept up and sent to the external model without anyone realizing. It happens.
Okay, yeah, that sounds easy to do accidentally. And you obviously can't read every single prompt going out.
No way, you can't. And this is why guardrails are the absolute first architectural component you need to add. Think of them as a safety layer.
Okay.
Their job is to mitigate these risks before the input hits the model, and also after the output is generated, but before it gets back to the user.
So what are these guardrails actually looking for? Specific words?
You configure them. Usually they look for PII, personal information identification. So phone numbers, bank accounts, names. But it could also be company secrets, project code names, maybe even faces and images. What counts as sensitive? You define that.
Right, depends on the context. And if they find something, block it.
Blocking the whole query is the simplest action, yeah. But you can be smarter. You can remove or mask the sensitive data, replace it with a placeholder, like phone number.
Okay.
And there's a clever pattern mentioned, sort of like in figure 10.3, where if that masked info appears in the model's output, you could potentially use a lookup to put the original sensitive data back in just before showing it to the user, because now it's safely back inside your system.
Ah, I see. So you sanitize it for the external call, but potentially restore it internally. That is clever. What about, like, abusive inputs or people trying to trick the model?
Guardrails handle that too. They can detect harmful language, prompt injection attempts, ignore all previous instructions, kind of stuff. Or they can flag really complex or maybe risky queries and route them to a human review queue. You could even use sentiment analysis. If a user sounds really frustrated after a few tries, maybe hand it off to a person.
Makes sense. How are these things built? Are they just simple lists of bad words?
They can be simple rule-based things, yeah, looking for patterns, keywords, but they can also be embeddings-based.
Embeddings, like semantic meaning.
Exactly. So they catch variations of problematic stuff, not just exact phrases. Or, and this is interesting, they can be LLM-based.
You mean use another AI to check the first AI's input and output?
Basically, yeah. You use a separate specialized model to evaluate the input or output against safety rules, like checking for harmful content, impersonation attempts, trying to make the model ignore its main job, that kind of thing.
Wow. An AI policing another AI? Okay. Are there tools for this? Off-the-shelf stuff?
Yeah, definitely. Sources mention things like Meta's Purple Llama, NVIDIA NeMo guardrails, Azure has AI content filters, and Pirate, there's Perspective API, OpenAI's Moderation API. Some gateways might include basic guardrails too.
Okay, so bottom line. For you building production Gen AI, guardrails are step one, non-negotiable. Protect the users, protect the data. Foundational.
Absolutely. Day one stuff. Okay, so now imagine your app grows. You're not just using one model anymore. Maybe you need a big, powerful one for complex stuff and a smaller, faster, cheaper one for simple queries.
Right. Or maybe you want to use models from different companies. OpenAI for one thing, Anthropic for another.
Exactly. And now suddenly you're juggling multiple APIs, different ways to authenticate, different costs, different speeds. It gets messy really fast.
Yeah, I can see that. Your application code starts getting cluttered with all this provider-specific logic.
That's precisely where the model gateway comes in. Think of it conceptually, like Figure 10 and Nut 6 shows, as a single unified entry point, a wrapper between your applications and all those different models.
So my app just talks to this gateway thing, and the gateway handles routing it to the right model.
That's the idea. It's a critical abstraction layer, and the benefits are pretty significant. First, like you said, a unified API. Your app devs don't need to learn 5 different SDKs. They just talk to the gateway.
Okay, that alone cleans things up a lot.
Big time. And it centralizes control. The gateway becomes the single point for access control authorization, instead of scattering API keys all over your code base.
Which is a security nightmare waiting to happen.
Totally. You manage access at the gateway. It decides who gets to use which model. Much safer. Reduces the risk of leaking those precious tokens.
And cost. You mentioned cost earlier. These models aren't free.
Yeah, this is a huge win for gateways. Centralized cost management. You can monitor usage across everything, see which teams or features are spending what, attribute costs properly.
And you mentioned optimization, like weighted load balancing. How does that work for cost?
Right. So imagine you have, say, a $100 budget. You can use a fancy model at $1.20 a pop, or a quicker, cheaper one at $5. The gateway can split the traffic based on weights you set. Maybe send 80% of requests to the cheap model, 20% to the expensive one. It mixes the traffic to stay within your budget over, say, 1,000 requests. Just an example calculation, but you get the idea.
Got it. Managing the blend to hit a budget target?
Yeah.
Smart. What about just raw performance, handling lots of users?
The gateway helps there too. It can manage rate limiting, throttling so you don't accidentally DDoS the downstream APIs or even your own systems.
Right. Smoothing out the load.
And it's the logical place to handle scaling. Maybe routing requests across multiple instances of the same model, or setting up fallback policies. If your main model provider is having a bad day,
it automatically tries a backup.
Exactly. Routes the request to an alternative model automatically. Builds in resilience.
And logging, I assume.
Yep. Natural place to centralize all your logging and analytics for every model interaction. Super useful for debugging, understanding how things are being used. Some gateways even bundle caching or basic guardrails, though often a dedicated guardrail layer is better.
So looking at the architecture diagrams, like 10.7, the gateway just slots in there between the application logic and all the different model options. It's the traffic cop.
Perfect way to put it. For you building stuff out, adding a model gateway is how you manage complexity, tighten security, control costs, and add flexibility and resilience, especially once you move beyond just one model.
Okay, so we've got safety locked down with guardrails, we've streamlined access with a gateway, but standard LLMs, they only know what they were trained on, right? Their knowledge is frozen in time.
Pretty much, yeah. They don't know about last week's news or your company's latest internal docs or, what this specific user was just talking about 5 minutes ago.
And they can just make stuff up, the hallucination problem.
Exactly. Confidently wrong sometimes. Direct prompting alone hits a wall pretty quick. And this is the problem that Retrieval Augmented Generation, or RAG, is designed to tackle head-on.
RAG, okay. It feels like it's everywhere now. But how do you explain it simply? What's the core idea?
The sources often use this analogy, and I think it's pretty good. Imagine you have a super smart, articulate person, like a junior researcher.
Yeah.
But their general knowledge is maybe a bit dated.
Okay.
You have a specific, complex question for them. Before you ask, you hand them a binder, a really well-organized binder full of the most relevant, up-to-date documents specifically about your question.
Right. A briefing packet.
Exactly. And you say, okay, read this binder first. Then answer my question only using the information you find in here. If the answer isn't in the binder, just tell me. That's basically what RAG does for the LLM.
So you're fetching relevant external info at the time of the query and giving it to the model as context. How does the system find that binder info?
It's usually a two-step process before the final generation.
Yeah.
First, indexing.
Indexing. Yeah.
You take your knowledge base, could be documents, website content, internal wiki pages, whatever, and you break it down into smaller pieces, chunks.
Manageable chunks.
Right. Then you use something called an embedding model. This model turns each chunk of text, or even images sometimes, into a list of numbers, a vector, an embedding.
Okay, like a mathematical representation.
Exactly. And the key thing is, this embedding captures the semantic meaning of the chunk. Chunks with similar meanings will have vectors that are close to each other mathematically in this high-dimensional space.
So electric car and battery-powered vehicle would have similar embeddings, even though the words are different.
Precisely. It's about meaning, not just keywords. That's the magic. Then you store these chunks, along with their embeddings, in a special kind of database, usually a vector database, designed for super-fast similarity searches.
So you've built this searchable index of your knowledge, represented by these meaning vectors. Then the user asks a question.
Right. Now comes the retrieval phase. You take the user's query, and you use the same embedding model to create a vector for it. Then you go to your vector database and say, find me the document chunk embeddings that are most similar to this query embedding. The database uses fast search algorithms, usually approximate nearest neighbor, to find the closest matches.
So it finds the chunks that are semantically closest to the question?
Yep. And then you retrieve the actual text of those most relevant chunks. That's your binder content.
And finally, generation.
You put it all together. You create a special prompt for the main LLM. This prompt usually includes the original user question plus the text of those chunks you just retrieved. And critically, you instruct the LLM. Answer the question based only on this provided context. If the answer isn't here, say so.
That totally changes the game for what the LLM can talk about.
Absolutely. It makes a general model suddenly smart about your specific, potentially private or rapidly changing information. The benefits are huge. You can use real-time data just by updating your index. You massively increase factuality, reduce hallucinations, because it's grounded in sources.
Less making stuff up.
Right. You can potentially mitigate biases from the original training data.
Yeah.
And you leverage the model's ability to learn in context from the text you provide right there in the prompt.
How does this compare to fine-tuning? Like training the model itself on my data. Isn't that another way to make it know my stuff?
It is another way, but the sources are pretty clear. Raji is almost always the place to start. Fine-tuning involves taking the base model and doing additional training on your specific data set to actually change the model's internal weights.
Okay.
That is way, way more resource intensive. It's expensive, takes a lot more time, requires significant compute power, and crucially, a ton of effort in preparing and cleaning that training data.
More effort than just indexing documents for a RAG.
Much more. One source mentioned a legal model project, NATAP. The fine-tuning itself took maybe 88 hours, which is a lot, but the whole project was 4 months. And almost half that time was just data prep for the fine-tuning. RAG is comparatively much faster to get going and easier to keep updated.
Wow. Okay, so RJ is more about giving the model access to facts at query time, while fine-tuning is more about deeply changing its style or its fundamental understanding of a domain.
That's a really good way to put it. You typically only consider fine-tuning if RJ just isn't cutting it on your evaluation metrics and you need a fundamental shift in how the model works or writes, something providing context alone can't fix. For most use cases, RJ is the practical, efficient choice.
So for you listening, RJ is really your go-to tool for making a general LLM smart about your world, your data.
Definitely. Now, while that basic Arch process is powerful when you try to use it in the real world, you hit some limitations. Just doing that simple search and prompt doesn't always get you the absolute best results consistently.
Right. What kind of limitations?
Well, the sources talk about these emerging patterns for building more realistic Arch systems, stuff shown on more complex diagrams. One big issue is inefficient retrieval. A simple vector search might miss relevant stuff if the user's query uses different words, or if the key info is maybe in a table or structured differently.
So how do you improve the retrieval part?
You often use a hybrid retriever.
Yeah.
Instead of just vector search based on meaning,
Yeah.
you combine it with good old-fashioned keyword search like TF-IDF or BM25, running on a standard text index. Keyword search is great at finding exact matches, specific terms or codes that semantic search might gloss over.
Ah, okay. Best of both worlds.
Pretty much. You pull candidate documents from both search types, combine the results, and you usually get a much richer set to work with. This hybrid approach might even involve querying different types of databases, like pulling structured data from a graph database alongside unstructured text from your vector store.
Using the right tool for the right kind of data search. Makes sense. What if the user just asks a really short, vague question?
That's the minimalistic user query problem. A common solution here is query rewriting.
Query rewriting.
Yeah. So before you even hit your knowledge bases, you make a quick call to an LLM. You give it the user's original, maybe vague query, and ask it to generate several different ways of phrasing that question. More specific versions, alternative phrasings.
I see. Expand the query first.
Exactly. Then you perform your retrieval step using all of those generated queries, not just the original one. Massively boosts your chances of hitting the relevant documents.
Okay, that sounds powerful, but another LLM call.
Yeah.
That adds cost, right? And latency.
Oh, absolutely. It's a clear trade-off. You have to measure it. Is the improvement in retrieval quality worth that extra cost and delay for your specific application? Sometimes yes, sometimes no.
Right. And I've heard about this lost in the middle issue, where even if you retrieve good stuff, if you give the LLM a really long context window filled with many documents, it might ignore the important bits if they're buried somewhere in the middle.
Yeah, that's a known limitation of current LLM's attention mechanisms. The fix here is adding a re-ranker step.
Re-ranker, okay?
So after your retriever, hybrid or simple, pulls back maybe, say, 20 candidate chunks, you don't just stuff them all into the final prompt. Instead, you path those 20 retrieved chunks and the original user query to a separate, smaller, specialized re-ranker model.
What does it do?
Its only job is to look at each retrieved chunk and score how relevant it actually is to the specific query. It then reorders the chunks from most to least relevant.
Ah, okay.
Then you only take the top, say, 3 or 5 highest scoring chunks, and those are what you put into the final prompt for the main conversational LLM. It filters out the noise and puts the best bits right at the top. You could even incorporate user preferences or other signals into this ranking.
So it's not just finding stuff, it's making sure the most useful bits of that stuff get prioritized for the LLM.
Precisely. And finally,
Yeah.
where do our guardrails fit into this more complicated R-Rage pipeline?
Ah, right. They still need to be there, yeah. At the start and the end.
You got it. Absolutely essential. Yeah. Input guardrails run before anything else. Before query rewriting, before retrieval. Catch malicious inputs or prompt attacks right at the door.
Stop it before it messes with the R steps.
Exactly. And then output guardrails run on the final response from the main LLM before it goes to the user. Double-checking that no sensitive info slipped through from the retrieved context or that the LM didn't generate something problematic on its own.
Another layer of safety. Again, adds a bit of latency and cost, but probably worth it.
Usually, yeah. The risk mitigation is key for production. So if you visualize the whole flow now, it's a real pipeline.
Yeah, it's like query input guardrails, check it, maybe query rewriting expands it, hybrid retriever searches vector and keyword stores, results get aggregated, re-ranker filters and sorts, then the top context goes to the main conversational LLM, its response gets checked by output guardrails, and then finally back to the user.
That's the picture of a realistic production-grade RA system. It's way beyond that first simple diagram. These advanced patterns are often necessary to get the accuracy, robustness, and safety you need.
Okay, so we have this sophisticated ARG pipeline, but even then, production traffic is messy. It's bursty, unpredictable. Models can be slow sometimes. They hit rate limits. Maybe the API even goes down for a bit. How do you make the whole thing resilient and scalable?
Right. Now we're talking engineering for scale and reliability. The sources emphasize having a dedicated AI service layer, separate from your main application logic. Like that Globomantics news example, the AI summarization part was its own service.
Why split it out? Why not just have the R8 pipeline call the models directly from the main app?
Decoupling. It's key. Your main application shouldn't need to know about model rate limits or which specific model API to call or how to handle fallbacks. The dedicated AI service encapsulates all that AI-specific complexity.
Ah, so they can scale independently. The main app handles users, the AI service handles models.
Exactly. And they can evolve without breaking each other.
Yeah.
Inside that AI service, you need smart ways to manage the load across different models or instances. Load balancing.
We talked about weighted load balancing for cost.
Yep. Great for cost optimization using cheaper models more often, or maybe latency optimization by favoring faster models during peak times.
But what if the requests themselves are very different, like asking for a one-sentence summary versus summarizing a massive report? Sending both to the same cheap, fast model might not work well.
Good point.
Yeah.
That's where payload-based routing comes in. The AI service looks at the incoming request itself, like how long is the input text,
Okay.
and routes it based on that. Short inputs might go to a fast, cheap model. Really long inputs might go to a more powerful, maybe slower model that has a larger context window or is better at complex summaries. You optimize based on the workload.
So you pick the routing strategy, weighted, payload, maybe a mix that fits your application's traffic and needs. But what about just sudden spikes, everyone hitting it at once?
Yeah, bursts can kill you if you just pass everything straight through. They cause cascading failures. The solution is queuing and rate limiting.
Okay, how does that work?
Requests arrive at your AI service. Instead of going straight to the model, they go into a queue, like a waiting line.
Right.
Then, a separate process pulls requests off the queue at a controlled pace, say no more than 5 requests per second, whatever your downstream models or your budget can handle, and then sends them to the model API. It smooths out the bursts.
Controls the flow downstream. What if the queue gets too long?
Crucial point. You set a maximum queue size. If the queue's full when a new request arrives, you reject it immediately. Send back a 429 too many requests error.
Fail fast.
Exactly.
Nice.
The sources stress this. It's much better to tell the user we're busy, try again in a moment, than to have them wait indefinitely for a request that might eventually time out anyway. It gives predictable behavior under load.
Okay, queuing and rate limiting for handling bursts. What about outright failures? The model API just errors out or goes offline.
You have to plan for it.
Yeah.
Models will have issues, downtime errors, super slow responses. A single point of failure there is bad news for a production system.
So redundancy, fallbacks.
Yep. You need mechanisms to handle this, often managed by a component within the AI service, sometimes called a model selector. Its job is to watch the models.
What's it watching for?
Key health metrics. How many requests to this model failed recently? How many were unusually slow? You define thresholds.
Then if a model crosses a threshold, bad health.
The model selector automatically, temporarily takes it out of rotation, marks it unhealthy. Any requests that would have gone to it are now rerouted to a predefined backup model, one that's currently healthy.
Automatic failover.
Exactly. Some setups might even have a last resort where if the backup is also down, it might try the original unhealthy one again just in case it came back online. Better than failing entirely.
So building resilience means actively monitoring model health and having those backup plans ready to go automatically.
That's the core idea. For you building these systems, this engineering for scale AI services, load balancing, queuing, rate limiting, fallbacks, this is the stuff that turns a fragile demo into something that can actually handle the real world reliably.
Okay, wow. We've built up this incredibly layered system. Guardrails, gateway, advanced RG, scalable AI services. It's complex, but once it's running, how do you actually know it's working right? And, maybe more importantly, how do you figure out what broke when it inevitably doesn't work right?
Yeah. That brings us to the crucial part, operationalizing it. And thinking about responsible design. Specifically, let's talk observability.
Observability, different from just monitoring.
Yeah, the sources make a nice distinction. Monitoring is like tracking known outputs. What's my latency? What's the error rate? Observability is about designing the system from the start so you can understand its internal state just by looking at its external outputs, its logs, metrics, traces.
So you can diagnose unknown problems.
Exactly. It's about instrumenting your system so you can ask questions you didn't even know you'd need to ask when things go sideways. It lets you peer inside the machine.
Okay, what are the goals here?
Two main things. Mitigate risks, failures, security problems, performance issues, model drift, and also discover opportunities, find ways to optimize cost, improve performance, understand how users are really using it.
Are there standard metrics?
Yeah, the field borrows heavily from DevOps. Key metrics like MTTD, mean time to detect an issue, MTTR, mean time to resolve it, and CFR, change failure rate, how often your deployments break things. If your CFR is high, something's wrong with your testing or monitoring before you deploy.
Makes sense. What about metrics specific to Gen AI, since it can fail in weird ways?
Right. You need to track the unique failure modes. How often is the model hallucinating? You need metrics for that. How often does it fail to follow instructions or output valid JSON if that's what you need? Factual consistency, does the output match the RAG documents? Toxicity levels. How often are your guardrails firing? Are you seeing weird, abnormal query patterns that might signal an attack?
How do you even measure some of those, like hallucination?
It's tricky. Sometimes you use AI judges, other models, evaluating the output. Sometimes it's spot checks by humans. You need to decide at the right granularity, too. Track these metrics per user, per feature, per model version, by time. You need that detail.
That sounds like a lot to track. How do you connect it all when something goes wrong?
That's where tracing comes in. It's the ability to follow a single user request all the way through that complex pipeline we built.
Ah, see every step it.
Exactly. Input guardrail, query rewrite, doc retriever, doc re-ranker, LLM call, output guardrail. If you get a bad result, tracing tools like Langsmith conceptually let you visualize that path and pinpoint exactly which component messed up. Was it bad retrieval? Did the re-ranker drop the ball? Or did the final LLM just hallucinate? Tracing tells you where to look.
Invaluable for debugging.
Totally. You also need drift detection monitoring for subtle unintended changes. Did the system prompt get changed accidentally? Did a model provider subtly change their output format? You need to catch that drift.
Managing this whole pipeline, all these moving parts, it feels like it needs its own management system.
It often does. That's where AI pipeline orchestration tools come in. Frameworks designed specifically to define, execute, and manage the flow between all these components, models, databases, tools, guardrails, especially as you build more complex agent-like systems. They keep the data flowing correctly and manage the multi-step logic.
Okay. And finally, beyond just making it work technically, what about the people using it, the responsible side?
Super important. The sources really stress this. Responsible AI design isn't an add-on. It's integral to the architecture. Thinking about real user needs. Designing for co-creation, letting users refine or steer the output. Building appropriate trust, being clear about what the system can and can't do, explaining its limitations. And designing for imperfection, making it easy for users to correct errors or provide feedback.
So it's not just functional, but actually helpful, safe, and ethical.
Exactly. These principles have to be baked in from the start. So for you listening, operationalizing means getting that visibility with observability, metrics, tracing. And responsible design means building and running that powerful system with user needs, safety, and ethics front and center.
We've definitely covered a lot of ground. We went from that super simple query response idea and layered on guardrails for safety, a model gateway for control, sophisticated arghi patterns for knowledge, AI services with load balancing, queuing, fallbacks for scale and reliability.
And wrapped it up with observability and responsible design for actually operating the thing well.
It really highlights that building production Gen AI means embracing this complexity. Each piece solves a real critical problem you will hit outside the lab.
Absolutely. A demo just doesn't face these same pressures.
And it makes you think. As these patterns get more mature, maybe become standard services offered by cloud providers, the line between what we call the model and the system around the model gets really blurry, doesn't it?
It really does. The intelligence is increasingly in the whole architecture, not just the core LLM.
Which leads to a final thought for you to chew on. As more of these complex architectural components become standard platforms or managed services, how does the role of you, the data scientist, continue to change? What new skills, what areas of focus are going to be most critical in this landscape? Is it more about system design now, evaluation, orchestration?
It's a fascinating question, and honestly, we've only scratched the surface here today. The sources we looked at go way deeper into the nitty-gritty of actually implementing and tuning all these patterns.
So definitely keep exploring, keep experimenting with these ideas as you build out your own robust production-ready generative AI applications.